If a function is continuous, does that mean it's differentiable? Not always. Today, we'll explore the three critical situations where derivatives break down and calculus hits a wall. A function is differentiable at a point if it meets two essential conditions that work together to ensure smoothness. First, continuity. The function must be continuous at that point. And secondly, the left-hand derivative and right-hand derivative must exist and be equal. Here's our first case. Corner or cusps. If the graph suddenly changes direction, creating a sharp corner where the slope shifts abruptly, the function is not differentiable at that point. For example, if we take the function f of x equals absolute value of x, at x equals 0, the function has a sharp corner. The left-hand slope equals -1, where the right-hand slope equals +1. Since these slopes are different, f prime of 0 does not exist. So here's the key takeaway. Corners mean different left and right slopes, which means the function is not differentiable at that point. Here's a second case, a vertical tangent. In this case, the graph is smooth, but the slope becomes infinite. This creates a vertical tangent line where the derivative cannot be defined. For instance, if we take the function f of x equals cube root of x, as we can see in the graph above, the function changes concavity when x equals 0. If we take the derivative, f prime of x will be equal to 1 over 3 times x to the power 2/3. And we know that at x equals 0, the denominator will be 0, and therefore the slope goes to infinity. So in this case, infinite slope equals vertical tangent, which means not differentiable. Here's a third case. Discontinuity. There are three types of breaks. A hole, that is a removable discontinuity where a point is missing. A jump, where the function suddenly leaps to a different value, as we can see here, when x equals 0. Or an asymptote, that is when the function approaches infinity. So in this case, at x equals 2, we have a vertical asymptote. Consider this piecewise function that demonstrates a discontinuity. F of x equals x squared when x is not equal to 1, but f of x equals 5 when x equals 1. If we look at the limit at x equals 1, the limit equals 1. However, the actual value of the function at x equals 1 is 5, and therefore the function is not continuous, therefore not differentiable. Differentiability requires continuity first. No continuity means no derivative. So here's a summary when derivatives break down. If you have a corner of or a cusp, the function is not differentiable at that point. If you have a vertical tangent, the function is also not differentiable at that point. And if you have discontinuity, the function is definitely not differentiable at that point. But if your graph is smooth and continuous, then the function will be differentiable at that point. Here's a challenge for today. Determine whether the function is differentiable at the given point. We have the function f of x equals absolute value of x minus 2 at x equals 2. So take a moment to think about it before moving forward. What type of situation does this represent? What would be the left hand and right hand slopes at that point? And consider how the absolute value function behaves on either side of x equals 2. You can take a moment to pause the video before looking at the solution. So here's a solution. This is a corner at x equals 2. The left-hand slope, you can see that it's negative at x approaches 2 from the left, and it's positive as x approaches 2 from the right. Therefore, the function is not differentiable at x equals 2. Differentiability is fundamentally about smoothness in the graph. If the graph can be drawn smoothly with one stroke, if the graph breaks, bends sharply, or shoots straight up, the derivative does not exist. Thanks for watching. Please like and subscribe to keep learning from us. And don't forget, math success starts when you stay on the fast track.